right, so last week, you guys should have finished up the rational exam. So we didn't have a lesson last week, but yeah, you had the exam of irrational equations last week, so I should be done with that. So let's look at what our last unit's going to be here. School's almost done. We don't have much time left. Seniors only have this week and next week, so it's like there's really not much time left for the seniors. So that means we don't have much left either. We do have one senior in this class, actually, who's only got 2 weeks left. But, all right, I'm going to put this up on the screen, guys. Let's go to our grade screen. I, of course, did not take the exam last week, so I still got to get that turned in on my account here. But you should have the rational equation exams. You should be all the way done with Module 6, which only leaves Module 7 for us. So this week, we're going to look at arithmetic sequences and series. Next week, we'll look at geometric sequences and geometric series. And that'll just leave us for the test and the final exam, which will be right after that. So we only have, what, 3 weeks? 3 weeks of lessons here. So 2 weeks of lessons and then the test of the sequences of series. Sequence of series goes quick. We're just looking at arithmetic and geometric. So we'll look at 7.01 this week. Get your pencil and paper. Let me tell you now, you'll want notes. There are some formulas that we use for arithmetic sequences, for arithmetic series, that make this really easy if you have these little formulas. Without the formulas, you're like, oh man, how am I supposed to figure it out? It's really, really hard. What am I doing? Because let me just kind of give you a preview of what we're looking at this week. An arithmetic sequence. 1, 2, 3, 4, 5, 6. That's an arithmetic sequence. To find the next number, you just add 1 to the number before it, right? It's a sequence of numbers that all, there's a difference of 1. Or we could say 2, 4, 6, 8, 10, 12, 14. That's an arithmetic sequence. Every time you just add 2 to the number before it and get the next number. So it's really easy. And I say, okay, if I have an arithmetic sequence, which goes 2, 4, 6, 8, 10, tell me the 8th number in that sequence. Well, you could probably do that pretty easily, right? But if I had a sequence that was like 1, 4, 7, 10, and I say, tell me the 71st number in that sequence, you might go, oh, well, that's going to take a while. And you'd have to sit there and write them all down until you get to the 71st one. These formulas give you shortcuts to where we can put in the numbers and jump straight to the 71st. That's why you want to make sure you've got these in your notes. So let's take a look at that. I'll put it back up on the screen. So you want notes on these, and it makes it real simple. All right, I'm going to close Module 6 because we're done with that. Open Module 7. Arithmetic sequences and series lesson 7.01. All right, we got a little activity right off the bat. So I'm going to have the chat window open. Tell me the next 3 terms in this sequence. So this is our arithmetic sequence. 8, 23, 38, 53, something, something, something. What are those 3 somethings? And I'm going to make this a little bigger on the screen because I want you to be able to see it. I know sometimes it's hard to see that on the presentation. By the way, my presentation allows me to zoom in. I don't know if yours does or not, but I could actually zoom in on the presentation. So, all right, you guys are on top of this. Oh yeah, Anthony's even got our difference here. Yeah, it's adding 15 every time. So we got 68, 83, 98. Submit. Perfect. All right, how about this one? -5, -7, -9, -11. What's the next 3 numbers in the sequence? It's counting by -2s, right? So negative 5, negative 7, negative 9, negative 11, negative 13, negative 15, negative 17. Perfect. Oh, little different. I'm not going to say it's any harder. It's just different. 3, 1.75. 0.5, negative 0.75. So still, it's got the same difference between every term. It's counting by the same amount every time. It just takes a little bit more math when we've got something besides whole numbers. So you just have to look to see what's it doing from this number to this number. Well, it starts at 3 and it goes to 1.25. So it went down negative 1.25. And then what to do from 1.75 to 0.5? It went down 1.25. And then when we subtract another 1.25, we get here. So if we subtract another 1.25, it gets us to negative 2. We subtract another 1.25. We subtract another 1.25. Just following the pattern there. And finally, this one. 2.5, 3.25, 4. I'll give you a second if you're calculating. So again, this shouldn't be something that should be hard as long as you're paying attention to the details. What's happening each time? Well, this is going up by 0.7. If you don't know how much it's going up by, subtract. Go to this one and subtract 2.5 from it. 3.25 minus 2.5 is 0.75. So every time it's going up by 0.75. Wonderful. All right. Bring this back down a little bit. Notice that the terms within each sequence were separated by a common difference. In 8, 23, 38, 53, which is the first ones we had, the terms 8 and 23, 23 and 38, 38 and 53, all have a common difference of positive 15. So each lists an example of an arithmetic sequence. So we're going to learn how can an expression or process be determined for an arithmetic sequence, what functions combine to create an explicit formula for arithmetic sequences, what possible restrictions exist in the domain and range, and how can expression or process be determined for an arithmetic series. A series is a little bit different. All right, an arithmetic sequence is a list of numbers, which we call terms, which share a common difference. So let's take a look at the following sequence. Some of these are arithmetic sequences and others are just sequences. So let me ask you, we'll make this a little bigger too. Is this an arithmetic sequence or not? It might just be a sequence of numbers. 1, 2, 7, 12, 28, 17, it's a sequence of numbers. What do you say, Anthony?
I have a question. For it to be considered an arithmetic sequence, does it change in between the values have to be the same every time, or can it change?
If it's an arithmetic sequence, it has to be the same.
Then I would say no, it's not an arithmetic sequence.
Yeah, that's correct. Because to be an arithmetic sequence, if it adds 1 here, it has to add 1 here and add 1 here and add 1 here. This is not. It adds 1, then it adds 2, then it adds 3, and adds 4. So it is not arithmetic sequence. So this is where we're trying to make sure we all understand this. An arithmetic sequence has to add the same number every single time. Now it could be a negative number, because we saw one that was negative 3, negative 5, negative 7, negative 9, negative 11, adding negative 2. So is this an arithmetic sequence? 3, negative 147, negative 297, negative 447. Yes or no? Is this arithmetic? Anthony says it is. Anyone else think on this one? Daniel agrees. So is it adding the same number every time? Yes, it's adding negative 150. 3 plus negative 150 is negative 147. Negative 147 plus negative 150, negative 297. Every time you can add a negative 150 and end up at the next number. How about this one? Oh, 10, 8, 12, 10, 14. I'll throw you a curveball here. Daniel says no. Anthony, no. No. 10 to 8, that's adding negative 2. But 8 to 12 is adding a positive 4. And then we added a negative 2 again. And then we added a positive 4. It's doing two different sequences at the same time. One of them, it's adding a negative 2. The other one's adding a negative 4. This is not an arithmetic sequence. It's a combination of two different sequences. How about this one? This is probably one of the easiest examples we're looking at. 4, 14, 24, 34. I think that one we can pretty clearly see. It's just adding 10 every time. Definitely an arithmetic sequence. So great job. Great job. The last one we did there just adds 10. That's the common difference. That's the term we use, common difference, which means it's the same difference and they all have it in common. All the numbers have this same common difference. The first one was not arithmetic. Then we had the one that added negative 150, and then we had this one that was negative 2 plus 4, negative 2 plus 4. All right. Let's go to page 2. All right, now, this is something you may see. All three of these, we got a list of terms, 3, 6, 9, 12. We got a table, 1, 2, 3, 4, 3, 6, 9, 12, and we have a graph. These are all the same arithmetic sequence. It's just a different way of showing them. It's a different way of displaying the sequence. This is the way we used to see it, the way we like to see it, 3, 6, 9, 12. We like to see a sequence of numbers just as a sequence of numbers with comments. That's great. But if you have it as a table, what the table is saying, n is the term number, which means the first term is 3. The second term is 6. The third term is 9, and the fourth term is 12. Now, we know that when we look at this list, we know the first term is 3, and the second term is 6, and the third term is 9. We just don't write it out where we say first term is 3, second term is 6. But we could do it with a table. And then we can take that table and put it on a graph. Look, the first term is 3, the second term is 6, the third term is 9, the fourth term is 12. So this is just 3 different ways of showing the exact same sequence. So if you can understand that, that makes things a lot simpler. It's like, oh, okay, so this is all the same thing. It's a sequence that has a common difference of 3, and it starts with 3 as the first term. So just understanding, we're talking about a sequence of numbers from the first term continuing forward. You will notice on the graph, this is a point about graphing sequences. There's not a continuous line through these points, right? When we look at this graph, it only has those points, but we didn't connect it. Remember, if you connect it with a line, that's saying every point on the line is part of that function. Well, if we connected it with a graph, that would mean that 1.5, 4.5 is part of the sequence. No, there's nothing between 3 and 6. There's not a 1.5 term. There's not a 0.2 term. There's only a first term, a second term, a third term, a fourth term, etc. But there's no terms in between there. So that's why we do not make this a continuous graph like on a line. We don't do that. This is called a discrete graph, and it's spelled discrete. It's finite. There are spaces between the points. Like the number of students in a class, it's a discrete set of data because only whole numbers can be used. We don't have 2.6 students in class today. Only a discrete number. So that's one of the big differences when we graph a sequence, is that we have to only graph the whole numbers. Okay, so there are two different methods for determining the terms of a sequence. Recursive is the easy one. The recursive process requires the use of the previous term. Like add 2 to get the next number is what you might say when you're thinking recursively. So if I give you a sequence and I say 2, 4, 6, it's easy to come up with the next term because you're like, okay, I just add 2 every time. That's thinking recursively, all right? And we might list that as a sub n, which a sub n means the nth term, which may be the fourth term in this case, equals a sub n minus 1 plus 2. Let me write that down because I want us to start recognizing what that looks like when we're talking about these n terms. So a sub n equals a sub n minus 1 plus 2. So if we have this sequence of numbers that I called 2, 4, 6, right? So we know that this is the first term. So we can call that a sub 1 for first term, because a is the term number. The term number. A sub n is the term number. So a is the term. Which term do I want? So if I want to know the fourth term, a sub 4, then I would take a sub 4 minus 1. I would take the third term and I would add 2. So when I look at this, first term, second term, third term, so a sub 4 would be 6, because that is a sub 3, that's the third term, plus 2. So we know the fourth term is 8. Right? And that's easy to see because I'm using a very, very easy sequence just to illustrate what this a sub n really is. N is the term number. It might be good to have in your notes. N is the term number. So a sub n. A sub, well, which term do I want? Well, I want the fourth one. So I changed the n to a 4. So this is asking for the fourth term in the sequence. And I use the third term to find that. 2, 4, 6, 8. And that's all fine. And we can find the fifth term, a sub 5, by finding a sub 4 and adding 2. Right? If we want to know the fifth term, we just take the fourth term, add 2 more. So we know it's 10 because this is 8 plus 2. So this is thinking recursively. So our recursive formula, here's one of our, we can go ahead and get this recursive formula. If we want to find any term in the sequence, all we have to do is take the term in front of it and add the common difference. E is the common difference. So there's our first formula. And we're like, hey, that's great. Yeah, if I know what the common difference is, and I can find the common difference real easy. I can see it's 2 on this one. And it's very easy for us to understand that if I want to find the 5th term, I just take the 4th term and add 2. I want to find the 5th term and take the 4th term and add whatever the common difference is, which happens to be 2. In this specific sequence, D is 2. So these are the things we need to understand on this. N is the term number. A sub n is where we find a specific term. N minus 1, that just means the term in front of the one we're looking for. D is the common difference. And this is all great until I say, okay, now tell me the 81st term. Well, we're going to get to a formula for that in just a moment. But this is talking about the recursive way. A sub 1 is 3, A sub 2, you take the first term and add 2, it's 5. A sub 3, you find the second term and add 2. So you get 3, 5, 7, 9, and that's just what I was showing on paper. Now there's something called the explicit formula. This is where I can jump straight to that 81st term. So the explicit formula allows you to calculate any term in a sequence directly, which is unlike a recursive process that requires that you know the term before it. So an explicit formula is useful in ways that the recursive process would be tiresome. Imagine if you were to ask to find the 45th term in an arithmetic sequence like 2, 9, 16. I mean, sure, it's possible to list all 45 terms, but that would take forever. All right, so let's figure out exactly how we would come up with something like this. All right, so we know, looking at this formula, so I'm going to write this down here. First term is 2. So we know our first term is 2 because we got 2, 9, 16, right? Move that out of the way. Ugh. I think it's my annoying. All right, so when we want to find the second term, see how they're doing that. So first of all, I'm putting here, we're looking at the sequence 2, 9, 16. Wow, that's the worst 9 I've written. 2, 9, 16. So the first term is this. The second term we can take the 2 and we'll add a 7. 1 times 7. So it's going to equal 9, right? So for the third term, if we started with the 2 and we added 7 twice, because we added 7 once here, we add 7 again here. 2 times 7 is 14. That'll give us 16. So that seems to be working. For this next term, if I add 7 3 times, 3 times 7 is 21 plus 2, 23. This process seems to be working pretty well. I just have to figure out how many times do I add that 7 to get to this term. So perhaps from that, we can get an explicit formula. So when we wanted to find a term, whatever the term was, A sub n, what did we use? What is 2? Well, 2 was the first term, right? That was A sub 1. So if we have the first term, a sub 1, and we added to it this is the common difference, right? So for this one, d equals 7. Every time it adds 7. And we can do this either way, and I think our text here does this way. How did we get 3 to find the fourth term? How did we get 2 to find the third term? This that we're adding to it, notice, is always 1 less than the term we're looking for. So if we take n minus 1 times the common difference and added it to the first term, that gave us the fourth term. So if we want the 45th term, we could take 2 plus n minus 1. N was 45, so we'll take 44 times the common difference of 7. So let's pull up our calculator so we don't make any mistakes on this. Okay, 44 times 7, 308, plus that 2. So the 45th term is 310. Because we just took, we added 44 sevens, right? We added 44 sevens to the first term to get the 45th term. That makes sense? Yeah, if I wanted the third term, I added 2 sevens. If I wanted the fourth term, I added 3 sevens. If I want the 45th term, I had 44 sevens. So this is our explicit formula where A1 is the first term. So let me highlight our 2 formulas here. So you can use whichever formula works best for the problem. If I give you a sequence that's just -2, -7, -12, and I say find the 5th term, well, you may want to use this one. I'll just find the 4th term and add this to it. But if I say find the 58th term, I'll probably want to use this one. I don't want to have to find all those other terms. So either one of these will work. It's just some of them are going to be a lot quicker to jump straight to the explicit than to try to use the recursive. If you've got those 2 formulas, that will help you with a arithmetic sequence, understanding how we got there, where those numbers come from, what is a sub 1, what is d, what is n. As long as you know those things, should make arithmetic sequences really easy. I'm going to give you just a moment while I cough and let you write that down. All right, don't make sequences hard, guys. You've been doing sequences since you learned how to count. 1, 2, 3, 4. That's a sequence of numbers. So we got ahead of it there, but to find the third term, we added 2 sevens. To add the fourth term, we added 3 sevens, etc., etc., etc. So where does the 2 come from? That's the first term. Where's the 7 come from? That's the common difference. What's the factor before the 7? It's the position of the term minus 1. So what's the 5th term? 30. And then, we can watch the little video real quickly. It's going to derive that formula that we should already have in our note.
Arithmetic sequence is 30. 30 can be rewritten as 2 plus 28. 2 represents the first term in the sequence, which is indicated as a sub 1. 28 is the difference between 30 and 2. 28 can be written as 4 times 7, where 7 represents the common difference between each term of the sequence. 4 is the result of 28 divided by 7. Use the variable d to indicate the common difference. 4 is the same as 5 minus 1. 5 represents the 5th term in the sequence, and 1 is the difference between 5 and 4. The variable n is used to represent the position of the term in the sequence.
All right, so there it is. There is that formula that we had already written down in our notes. I got this new pen feature here. I can circle it on the screen. Whew, I love it. Got this new little pen. Let's see. Do I have to have an eraser? Oh yeah, and erase it. I should use this other one. I got this little thing that is disappearing ink. It'll automatically disappear. But you should have it written down as the explicit formula right there. All right, let's close it back down. From this pattern, the formula for arithmetic sequences has been discovered. And then they want to make sure you know a sub n, a sub 1, n minus 1, and d. What are all of those? A sub 1 is the first term. N is the position of the term in the sequence. D is the common difference. And a sub n is the desired term you're looking for. So if you're looking for the 25th term, you have a sub 25 equals the first term plus 24 times the common difference, all right, which is 25 minus 1. So 170 would be the 25th term in the sequence without having to list them all, without having to do them one by one by one. Let's see. It also has, well, list them both right here. Here's both. If you didn't already have them written down from my notes, they're right here on page 2. A sub n equals a sub n minus 1 plus the common difference, or a sub n equals a sub 1 plus d times n minus 1.
In like 30 minutes?
And it says a sub n, n minus 1, and d are part of both equations. So you just know where to put them in the two different equations. All right, let's go to page 3. They say really what you should think about is this is a combination of functions. This is just a sub 1, it's just a number. So that's just like a straight, the explicit form of the combination of function, two separate parts, a sub 1 or the d n minus 1. Select either one to see more. It's a constant. A sub 1 is a constant. It's the first term. That's never going to change. For your sequence, the first term never changes. Whatever the first term is always going to be the first term. It's like money in a piggy bank or the number of windows in the house, right? You always have, it starts with this. This is where it starts with. That's what it started. You could change that. You could add more money to your piggy bank. You can add windows to your home. You can take windows out of your home, but there's always a starting out. And then the second part, d n minus 1, this is a variable expression because it's going to change as you move through the sequence. As your n changes, if I look at first term, second term, third term, fourth term, that's going to change what that's equal. So when we put those together, just add them back together, that gets us to our explicit formula. We're going to talk a little bit about domain and range because we always talk about that in math, right? The domain is the x's, right? That's all. If you think about it, if you graph this, let's go back to thinking about that graph of those numbers we saw back on this page. Let's go back to page 1 and look at, page 2, this graph. If we think about the domain is all the possible x's for any sequence. And this sequence is fine. We'll use this one. And the range is the possible y's. So for any given sequence, if we turned it into a graph instead of just a list of numbers, think about what are the possible x's. Now remember, to graph it, we would take a list and we turn it into a table where we'd have first term, second term, third term, fourth term, and list all the values. And then we would graph that. Can you think of any number that would not be in the domain of the graph of an arithmetic sequence? If we were to graph any arithmetic sequence, we could graph the 2, 9, 16 that we looked at, the 2, 4, 6, 8, 10. We could graph the -2, -7, -12. But for the x's, the domain, what could we not? Is there any? Can it be any possible number? We're going to dig in this a little bit more because we haven't really talked this out enough to really, maybe you don't have a good idea on this yet. I just want to see what you're thinking right now so I can kind of take this conversation in the right direction. So type something out for me. What are you thinking? Is there anything that could not be on the x-axis when we graph it? Daniel says 0. Okay, I like what you're saying, Daniel. Just tell me, why can we not have 0 in the domain? I'll tell you this, first off, you're correct. 0 would not be in the domain. Can you think of why we could not have 0 in the domain?
Is it because it's not an integer?
Because there's not a what?
An integer.
There's not an integer? Well, 0 is technically an integer. It's not a positive integer. It's not a decimal. Okay. You're right there at it, though. I think you're right at it. Tell me this, looking at this graph, what does the 1 represent on the when it's graphed right here? Why does it say 1? Why is that 2, 6? What's the 2?
Other questions before we continue?
3, 9. What is that 3 telling us?
Okay, make sure you are double checking your
It's the value of x.
8th grade.
Okay, what's it telling us in the table next to it? 1, 3, 2, 6, 3, 9. What is the n?
It's the term number.
It's the term number. So the term number, the second term is 6, it's telling us. Term number 2 is 6. Term number 1 is 3. So why can't we have a 0? What's term number 0?
It's not anything.
There's not a term number 0. So in the domain, we can't have term number 0. How about 0.7? We can't have a 0.7 term. How about -2? What's the negative second term? So the domain of an arithmetic sequence is going to be the same for every single arithmetic sequence. It's going to be integers greater than 0. Or you could say integers greater than or equal to 1. Because you can only have first term, second term, third term, fourth term. You can't have a 1.6 term. You can't have a 0th term. You can't have a negative fourth term. It has to be 1, 2, 3, 4, 5. That's the domain of every single arithmetic sequence. Starts with 1, starts with the first term. And it always goes up by integers, 1, 2, 3, 4, 5. That kind of makes sense? Kind of why we only have integers as the domain. The sequence is a set of numbers, and we count the terms as the first term, second term, and so on. So it would not be appropriate to have a negative term, a decimal term, fraction term. The terms always start at 1. This is the first term. So the domain for arithmetic sequences, and this is for all arithmetic sequences, is restricted to all integers greater than or equal to 1. That's it. And there will be a question, like on the assignment or the test. I remember seeing this question, I think, more than once, talking about the domain. Yeah, it's just 1 and greater, because you can't have a 0 term. You can't have anything. It's the natural numbers, they call them, because that's the first thing we learn to count. All right. And remember, in the explicit formula, n minus 1 is used. So an integer less than 1 would result in a negative number. So, if n was 0, 0 minus 1 would be looking for a negative. And that wouldn't be in the sequence either. Now, what about the range? The range is the possible, looking back at this, the range of this is y is 3, 6, 9, 12. It's 3 and greater by 3s. But is the range restricted? Could it be negative for a different sequence? I'm talking about for any sequence, not a specific sequence. The range. Can your sequence be negative numbers? Yeah, we looked at some that had negative numbers. Could it be decimal numbers? Could it be fractions? Yeah, your sequence could be anything. You can have sequence with positive numbers, negative numbers, decimal numbers. 0 can be in your sequence. That is all legal. So the range is not restricted. It can be any number. It just depends on your sequence. Now, a specific sequence has a specific range. It can only be certain numbers if we're talking about a specific arithmetic sequence. But if we're just talking about arithmetic sequences in general, there's no restriction. All right, so let's look at a few examples just to make sure we got an idea of what's going on. Identify the 46th term. Oh boy, they really gave us a good one here. They did not start us out with something easy. I'm going to draw a line here because we're going to have to work this out. Sample number 1, the 46th term of a sequence where the first term is negative 22 and the 12th term is 77. All right. 46th. A sub 1. It's going to take a little work. Negative 22. A sub 12 is 77. So the first thing we see is both of our formulas, if we're looking at our formulas that we can use, we got to have the common difference. Both of them have to have the common difference. This one, you need the first term. This one, you need the term before. So if we're finding the 46th term, we got to have the 45th term and add the common difference, or the first term and the common difference. But either way, we've got to have the common difference. And what do we not have here? We don't know what the common difference is between A1 and A12. So you got to find the common difference. And this is how they do that. So they're going to use the first term and the 12th term using this formula right here, using the explicit formula. So let's do what they're doing here. Okay, we want to find the 46th term. They gave us the first term and the 12th term. If we go to the explicit formula, it says the 12th term, which we know the 12th term, let's say it's 77, right? So the 12th term is 77. 77 should equal the first term. Oh, we know the first term. Plus n minus 1. What was n? N was 12 because the 12th term. 11 times d. Look, we have a simple equation we can solve. One missing variable. Add 22 to both sides. So that 99 equals 11d. Divide both sides by 11. D equals 9. So now that we know the common difference, to find the 46th term, a 46th, we can again use our explicit formula. The first term plus n minus 1. N is 46. So we can do that math pretty easy. Times the common difference. A 46 equals 45 times 9 plus negative 22. Or I could have said just subtracted. So we had to do a little work to find the common difference. But it should be 383. There it is, 383. That was a good starting example here. Let's look at example 2. This has a library containing triangular bookshelves where each consecutive shelf contains four more, there's a common difference, 4 more books than the shelf above it. If the top shelf holds 7 books, how many books are on the 11th shelf? Okay. So we know the top shelf holds 7. And it says each shelf holds 4 more. So that's our common difference. And they want to know the 11th. That one's not too hard. They gave us everything we need to use our formula. A sub 11 equals the first shelf, 7. N minus 1. Well, N is 11. So this will be 10. And the common difference is 4. Well, 10 times 4 plus 7 should be 47 on the 11th shelf. Let's see what they got. Oh, then we go step by step. What is the first term of the sequence? Well, they said that the top shelf holds 7 books. So it's 7. And the next one says, what's the common difference? It said 4 more. So that tells us. What's the value of the variable n? Wants to know the 11th shelf. So that would be n. And how many books are on the 11th? That was the 47 that we came up with. All right, and there's another example if you need it. All right, here's a difference. Here's the difference between arithmetic series and arithmetic sequence. So, an arithmetic sequence we just saw is 2, 4, 6, 8. A series is 2 plus 4 plus 6 plus 8. It's adding it as it goes along. Adding the sequence, 2, 4, 6, 8. So for this, if we're wanting to know what's the sum of the first 4, or what's the sum of the first, so the sum of the first 4, 2 plus 4 is 6, plus 6 is 12, so the sum of the first 4 would be 20. It's a sum with a series. We're summing them, we're adding them together if it's a series. Series equals a sum. So this is going to get a little different. We're going to have a formula for this as well. So here they want to make sure you know the difference between a series and a sequence. So let's look at these numbers. 4 plus 14 plus 24 plus 34. This is a series because it's being added. 3, negative 147, negative 297. And you see the subtraction there, but there's a comma. Since there's commas, this is just a sequence of numbers like we just got through looking at. 1, 2, 3, 4, 5. Series or sequence. There's no addition, it's just commas. If there's commas, it's a sequence. Oh, look, no commas. This is a series, right? So series, we add them together. A sequence, they put commas just to separate them. All right, so we're going to look at this video with this little series real quick. All right, here we go. So this takes this series of numbers, and it takes the first and the last one and adds them together. 4 plus negative 11. Then it takes the next two, 1 and negative 8, adds them together. Then it takes the next ones, 2, negative 5, adds them together. So what it's doing is it's taking the entire group of numbers and it's pairing them up. It does them in pairs. It takes the first and the last numbers and adds them together. And then the second one and the next to last one adds them together. And the third one and the next to last one adds them together. So it's pairing them up, and you notice that every time it does that, it ends up with the same number. 4 plus negative 11 is negative 7. 1 plus negative 8, negative 7. Negative 2 plus negative 5, negative 7. That gives us a great idea on how to come up with totals. So on this, instead of adding those together, it's really just negative 7 times 3. Nice. All right, before we jump into this, I want to make sure we understand the definition of these terms again. That's not a bad thing for us to review. Let's see. A sub n. A sub n. Is that the last term of a sequence, the first term in the sequence, the number of terms in a sequence, or the common difference? I'll tell you what, let's skip that one and come back to it. Let's get some of these other first. A sub 1. A sub 1 we should definitely know, right? A sub 1 is the first term, right? A sub 1 is always the first term. That'll go away. What is D? D is always the common difference. So that gets us down to N and A sub N. One of those is the last term in a sequence. One is the number of terms in a finite sequence. Well, A sub n would refer to a specific term. That's what the little a is. That's what the a is. A sub n would be the last term. So if we had A sub 8, that would be the 8th term in an 8-term sequence. A sub n would be the last term. N would just be the number of terms. All right. Yeah, no, we don't need to restart that. We're okay. So it says, using some or all these variables, a sub n, a sub 1, n, and d, write a mathematical expression allow you to find the value of negative 7 from the series we just looked at in the video. Well, a sub 1 and a n. So let's play with that just a little bit on paper. So they went 4 plus 1 plus negative 2 plus negative 5 plus negative 8 plus negative 11. And they took the first term and the last term and added those together to get negative 7. All right, and then they took the next term there, and the next term there, and added those together, and it came up with negative 7. And I can't find anything now. That's gone for a week. Here we go. There's what I'm looking for. Then we took the next sets of terms and add those together to be negative 7. So if we wanted to say, using the terms we know, we took a sub 1 and added it to the last term, a sub n, because this is a 6-term series, so a sub n would be the 6th term, and we added those together to get negative 7. So it's okay. The expression is a1 plus an. And you know it's being multiplied by 3 using an, a1, n, and d. How do we come up with a 3? Well, this is 6 terms, right? So n equals 6. So if we multiplied this, divide n by 2, that'll give us our formula. N divided by 2, 6 divided by 2 is 3. 3 times a sub 1 plus a sub n negative 7, negative 21. So is that what this adds up to? 5 plus negative 2 is 3. 3 plus negative 5, negative 2, negative 10, negative 21. Yeah, these do add up to negative 21. So we might have just derived our formula from that. N divided by 2. It gives us last page here. Find the formula by working it backwards. Okay, they just want to have a little video.
The arithmetic sequence is negative 21. Negative 21 can be rewritten as 3 times negative 7. 3 represents the number of pairs in the arithmetic series, and negative 7 is the result of negative 21 divided by 3.
Around your house.
The 3 pairs in the arithmetic series can be written as 6 divided by 2, where 6 represents the number of terms in the series. Negative 7 can be written as 4 plus negative 11. 4 represents the first term of the series,
How old are you?
and negative 11 represents the last number of the series.
So yes, our formula for arithmetic series, define the total number of terms in the series divided by 2, first term and last term added together, and you multiply that. Multiply this times that, which they also have right here in our lesson. So let's see, they're having a practice problem here. Oh, and then they have a rewritten version of it in case, this is in case you don't have the last term. So let me show you how we got this one. So from this formula, if we don't have a sub n, we had a formula on the other notes on how to find a sub n, right? It's a sub 1 plus n1d. So we can just take the same formula, n divided 2, a plus 1, but instead of a sub n, we can substitute this in there. Because that is the formula that a sub n is. A sub n is the same as a1 plus n1 minus d. So then when we simplify this, we see we got a sub 1 plus a sub 1, so that's 2 a sub 1s. So n divided by 2 times, and all of this is in parentheses, 2 a sub 1s plus n minus 1 times the common difference. So this is just an alternate way to get this in case you don't have the last number of the sequence. That's it. I'll probably throw one of those at you, but most of the time you'll find yourself with all the information to use that one out there. Alternately, instead, if you don't like this, if they don't give you the last one, just go back here, use this formula, figure out what the last one is by yourself, and use this one. But that is an alternate formula if they don't give you a sub n, because you should have a sub 1 anytime on the sequence there. All right, let's see if they give us at least one example that we can play with here. Yeah, they give 4 practice ones. We'll do one of them here, and then I'll let you guys, we'll look at the assignment and go, what is the sum of a 44-term arithmetic sequence where the first term is negative 9 and the last term is 120? So we have the first term, we have the last term. The sum, oh, I don't need to put in because I know how many terms there are because they told us there's 44 terms. So the sum of those 44 terms is 44 divided by 2 times -9 plus 120. Okay. Let's see, -9 plus 120. No, that's I hit something different. So -9 times 120 is 111. So this is 22 times 111, or 2,442. There you go. And they'll show you how to work all that. But they give you 4 problems there you can look at. First term, last term. Last term's -16, so this one's going down as it comes. But they got 4 of those you can work. And there's the lesson summary. We should have all of our equations in it that we have in our notes. There's the arithmetic sequence formula. There's the recursive and explicit. And see, sometimes they put the D in front of the parentheses, and sometimes they put the D after the parentheses. It doesn't matter which way you write that. It's the same formula. And then there's the 2 arithmetic series equations. So let's take a look at the assignment. Identify the 35th term of the sequence. Here's the first term, and there's the 18th term. Find the 27th term of this sequence. The windows are arranged so each floor has 6 fewer. There's your common difference. Given these functions, f of n equals 11, g of n is -2n minus 1, combine them to create an arithmetic sequence formula. So it'd basically be 11 minus 2 times n minus 1, and find the 31st term. And given this arithmetic sequence in the table below, create the explicit formula, list any restrictions to the domain. I knew they were going to talk about that. But, oh, they don't give you any problems about series. These are all sequence questions. All sequence questions. Well, you'll need the series questions on the exam at the end for sure. But all the practice here is just with sequences this week. So they made it a little easy with the 5 questions. They're all sequence questions, no series questions. So, all right, guys, that's all I got for you. And we're about out of time anyway. So you guys have a great week. It is an A week, so I'll be here Wednesday and Friday. So if your grade's suffering, when you do your grade check, look to see which is highest between Hack and Buzz. I came back and have over 100 things to grade. When you're gone for a week, things pile up. So it's going to take me a couple of days to get the grade book updated. But if your grade is higher in Buzz than it is in Hack, great. Go with that in your grade check because that's more accurate because I am behind on grading now since I was out for a week. But I will get caught up this week, assuming that I don't get sick again. So have a great week, guys. We will see you next time.